and welcome to the fifth presentation of Elements of Neural Networks and Deep Learning, Part 5. I am Thiniyam B. Ganesh. So this presentation is based on material from Neural Networks and Deep Learning by Professor Andrew Ng at Coursera, and I also based it on other material from the internet. In my last presentation, presentation 4, I had shown how to derive the equations of a multi-layer, multi-unit deep learning network. And the four propagation equations are: the linear activation at the lth layer is the weight matrix at the lth layer into the activation function at the L minus 1 layer plus bias, and the activation function at the lth layer is g of zl, where g is some activation function, ReLU, tan h, sigmoid or Leakey ReLU, etc. And the backward propagation equations are dou L by dou AL, that is the activation of the lth layer, is dou L by dou ZL plus 1 into WL plus 1. Dou L by dou ZL is equal to dou L by dou AL into the derivative of the activation function at the lth layer G prime ZL. And dou L by dou WL is dou L by dou ZL into AL minus 1. And dou L by dou BL is dou L by dou ZL. The key motivation and the key driving thing in neural networks is to identify how the loss varies for changes in weight and bias. Once we know how the loss varies, then we use a technique known as gradient descent, where we iterate and determine the optimum set of weights that will result in the lowest cost or loss. And find the weights. Once you have the gradients, that is how the cost varies with respect to the weight, using a learning rate alpha, we compute the new weight for each cycle as w minus alpha into the gradient of the weight, and b as b minus alpha into dou j by dou b. Basically, if you can see this, we will go through one cycle of forward propagation, compute the loss, and in the backward propagation we will compute the gradients with respect to the weights and biases in each layer, and then we will use the gradient descent formula to make a change in the weight. Now with this new changed weights and bias, we will do another cycle of forward propagation, compute the loss, and in the backward direction we will compute the gradients and compute the new weights and biases. So we will go through the cycle iteratively, and finally we'll end up with a lowest cost for the neural network, which will be the optimum set of weights and biases for a neural network. Now so far, up from presentation 1 to 4, we only looked at binary classification, and we used the sigmoid function. Sigma of z is equal to 1 by 1 plus e power minus z, and this sigmoid function, we have seen it takes a value between 0 and 1. For multi-class classification, which is what this presentation is going to be about, we will use what is known as the Softmax function. The Softmax function is defined as S of j is equal to, for a given vector, is e power j of the jth element of the vector divided by all the elements of the vector raised to the power e. So let us look at this a little bit more closely. So for example, if you have taken a vector a is equal to 1, 3 and 6, and we take the softmax of this using this formula, you will get the values 0.0063, 0.0471 and 0.9464, and you will notice that these values are proportional to the actual values in the vector. So 6 is the largest, and you will find the softmax function as the largest value here, and next is 3, which has a slightly smaller value, and 1 is the lowest, and it will be the smallest value in the softmax. The vector is proportional to the input. And also, since we are dividing it by the sum of all the elements of the vector raised to the power e, the sum will always be equal to 1. Hence, this softmax output can also be considered as a probability. Now let us take a simple 3-layer network. We have inputs. We have the linear activation Z1 and Z2 at the layer 1, and then the activation function A11 and A21. And subsequently for layer 2 we have Z12, Z22, and at the output we have softmax S11 and S22, and we have the estimated loss. Now this can be represented using a matrix function. Z11 is equal to W11 subscript 1 x1 plus W21 superscript 1 x2 plus b1 superscript 1, and z2 2 to the w1 2 superscript 1 x1 plus w2 2 superscript 1 x2 plus b2 superscript 1. And then we have the actuation function at layer 1, which is g prime z11 and a2 g prime z2, okay, subscript 1. Similarly, we can do the same equations for layer 2, except that the actuation function at the layer 2 is the softmax function s of z1 subscript 2, s of z2 subscript 2. Now this vector s of z1 subscript 2, s of z2 subscript 2, we know that the softmax is given by the formula we had seen before here. So this is, we can write this as s is equal to e power z1 divided by e power z1 plus z2, the sum of all the vectors raised to the power e, and for z2 e power z2 divided by e power z1 plus z2. Now when you as I said, for computing how the loss changes with respect to the weight, we first need to find the derivative of the loss, and to do that we need to do the Jacobian. So since we need to find the Jacobian, so let us see how to find the Jacobian. Now we have two elements in the vector, and since we need to find the derivative, we need to take the derivative of this vector s1 with all the elements of the vector. So j is equal to dou s1 by dou z1 and dou s1 by dou z2. Similarly, the second this element will be dou s2 by dou z1 and dou s2 by dou z2. Now I rewrite this as dou by dou z1 of s1. S1 is e power z1 by divided by e power z1 plus z2, and dou by dou z2, again s1 is e power z1 divided by e power z1 plus z2, and dou by dou z1 of s2. S2 is e power z2 divided by e power z1 plus z2, and dou by dou z2 of e power s2, which is e power z2 by e power z1 plus z2. Now let us see how to do the derivative of this. I have just rewritten that same matrix here with the derivatives, and we use the chain rule. D by dx of u by v is equal to v du minus u dv divided by v square. Now let us assume that this denominator is by a symbol sigma, which is e power z1 plus e power z2. Now if you do the derivative, it's a bit laborious, even though I've just taken two input z1 and two input x1 and x2 and have z1 and z2. We can see that the derivatives dou z1 of ez1 divided by ez1 plus z2 and dou by dou z2 of ez2 by e divided by z1 plus z2, these two will have an identical form and these two will have an identical form. So if I take this, where I is equal to j, that is 1 1 and 2 2 element, let us take the derivative of this. Dou by dou z1 of e power z1 divided by e power z1 plus z2. So if you use this division rule, so I have sigma, which is the denominator, and dou by dou z1 of e power z1, which is z1, minus v minus u is e power z1, and dou by dou z1 of the denominator, which is will be again be ez1, so you'll get e power ez1 squared divided by v square. V is e power z1 plus z2, which is sigma, so it's sigma squared. And when I is not equal to j, that is if I take e12 or e21, so let us take one element here, dou by dou z1 of e power z, I take this ez2 divided by e power z1 plus z2. Now dou by so I first take b is sigma and du so it is dou by dou z1 of e power z2. Now dou by dou z1 of e power z2 is 0, and then I take u dv. U is e power z2, and dou by dou z1 of the denominator will be e power z1 divided by v square will be sigma square. Now this term which we had here when I is equal to j, I can rewrite. I take the first element e power sigma e power z1 divided by sigma squared as equal to, if I cancel out the sigma here, it will be e power z1 divided by sigma, and the second term e power z1 squared divided by sigma squared, I can rewrite it as e per minus e per z1 divided by sigma into e per z1 divided by sigma, and this term 0 minus e z1 e z2 divided by sigma square, I write as e per minus e z1 divided by sigma e z2 divided by sigma. And since e per z1 divided by sigma e per z2 divided by sigma is a softmax, I can now rewrite this whole equation as when I equal to j, this term will reduce to Si into 1 minus Sj when I is equal to j. So that is Si into 1 minus Si. That is, you will get this term. And when I is not equal to j, it is minus of e per z1 by sigma e per z2 divided by sigma, which is equal to minus Si Sj. Now since the softmax is also equal to the probability, we can take, I just replace S by P. So dou Pj by dou Zi is equal to Pi into 1 minus Pj when I is equal to j, and dou Pj divided by dou Zi is minus of Pi Pj when I is not equal to, just replacing S by P. As I said, since the sum of all the softmax values will be equal to 1, I just replace it by the value of P as a probability. So now substituting this, I get for P1 1 it will become P1 into 1 minus P1 using this formula Jacobian, and this will be minus P1 P2, this will be minus P2 P1, and for element 2 2 it will be using this one, it will be when I is equal to j, P2 into 1 minus P2. Now in the binary classification we saw the log loss. For when you have multi-class classification, the loss is known as the cross entropy loss, and is given as L is equal to minus sigma of yi log of pi. Okay, the value of the output label at yi and the probability of that label occurring. So since we had just 2 inputs, I'm just simplifying it. I'm saying it's minus log p1 plus minus y2 log p2. Now if I take the derivative of this with respect to p1, dl by dp1 is equal to minus of y1 p1, since log of d of dx of log x is 1 by x, and dl by dp2 is y2 of divided by p2. And in fact, if you take this formula and you apply it for binary classification, that is, you had only y, the output is either y or not y, which is 1 minus y, you can see that this formula reduces to the logistic loss formula, which is minus y by a divided by 1 plus y by 1 minus a. Now the derivative of the cross entropy loss, so dou L by dou Z1 is equal to dou L, since we have two properties P1 P2, it will be dou L by dou P1 by dou P1 by dou Z1, and dou L by dou P2 into dou P2 by dou Z1. Now since dou Pj by dou Zi is Pi into 1 minus Pj when I equal to j, and dou Pj by dou Zi is equal to minus Pi Pj when I is not equal to j, which is what we saw here. Hence dou L by dou Z1 is minus y by P1, because this is what we saw here. Dou L by dou P1 is minus y1 by P1, and P1 into 1 minus P1 minus y2 by P2, which is what we saw here, into minus that is dou P2 by dou Z1 is minus P2 P1. So now if I reduce this, if I multiply and reduce this, I'll get minus y1 plus y1 P1 plus y2 P1. And P1, if I take out P1 from here, I get P1 into y1 plus y2, and then this minus y1 term. Now since y1 plus y2 is the sum of all the values of the labels for any one particular output, it will always be equal to 1. So this becomes P1 minus y1. Similarly, dou L by dou Z2 is, I can rewrite as dou L by dou P1 by dou Z2 plus dou L by dou P2 by dou P2 by dou Z2. Now dou L by dou Z2, now this one we know as y1 by P1, and dou P1 by dou Z2, since these indexes are different, it will be minus P1 P2, and dou P2 by dou Z2, since it's I is equal to j, it will be P2 of the form P2 minus P2. If you multiply all of this and reduce it, it will again come to P2 minus y2. So you'll find that this here the value output was dou L by dou Z1 is P1 minus Y1 and dou L by dou Z2 is P2 minus Y2. In fact, you'll find, even though it's large and laborious, finally how the loss varies with respect to Zi, the activation layer at the previous layer is Pi minus Yi. So the whole thing reduces to this very simple form for the softmax as the output. So now let us take a real network where you have inputs x1 up to xn, and we have the first layer linear activation Z1 and the activation A1, and which then feeds into the second layer, which is Z2 as the linear activation, and A2 as the softmax output, and then you have the softmax loss or the cross entropy loss. So the equation here will be, for propagation will be Z1 is equal to W1x plus B, where x is this input vector plus the bias at the layer, and the activation A1 is equal to G of Z1, where G is any activation function, ReLU, sigmoid or tan H, and Z2 is equal to W2 A1, which is the previous layer, plus B2, and A2 is equal to S. We are using the softmax as the second layer of Z2. And the backward propagation dou L by dou W2 is equal to, using the backward propagation equations we have already seen, is equal to dou L by dou Z2 into A1. So here dou L by dou W2 is equal to dou L by dou Z2 and A1. In fact, if you want to see this formula, you can go to the very first slide. Dou L by dou Wi is the dou L by dou Z at the Lth layer into A L minus 1, which is what we have here. So at the dou L by dou W2 is dou L by dou Z2 into A1. So dou L by dou Z2 is, as I said, we have already derived that dou L by, it has a general form of P2 minus Y2 into A1, and dou L by dou B2 is dou L by Z2. Again, this is the generalized formula, is P2 minus A2, and dou L by dou A1 is dou L by dou Z2 into W2, and dou L by dou Z2 is P2 minus Y2 into W2, and dou L by dou W1 is again similar to this formula, it is dou L by dou Z1 into A0, and dou L by dou Z1 is equal to P1 minus Y1 into A0, and dou L by dou B1 is dou L by dou Z1, and dou L by dou Z1 is P1 minus Y1, and so we have this. Now all these formulas for backward propagation and forward propagation, and we can do gradient descent. So once we do this gradient descent, we can keep on iterating and we will get the lowest cost. So I have taken this example for multi-class classification, where we have three classes, this yellow, and it's a spiral, this slightly vermilion color, and this bluish color, as three classes, and I used my deep learning network with Softmax as the output for multi-class classification, and this is what I get. So in Python, when I implemented it, this is it got a very nice clean separation for all these three classes. This is in R, the class how it classified it, and this is an octave. So again, as I said, this may look a little somewhat this new line here, but actually, as I said, if you are able to change the hyperparameters properly, then you'll get a very nice clean separation for all the implementations. And I also did a MNIST classification. As you know, MNIST is a set of handwritten digits that's used in deep learning. It's also known as the Drosophila for deep learning because you can run your code and test it out. And for digits 0 to 9, so you can see when I ran the confusion matrix, I got these numbers for about, I think, close to 6,000 training sets, and on the test set for 1,000 test cases, I got a fairly good classification with the accuracy of 0.93, precision 93, and recall 93. Thank you, and that ends the fifth presentation on elements of neural network and deep learning. I appreciate it. Thank you.